So I just want to shoot a quick video going over the practice test. So I'm just going to get right into it here. Here's the practice test here. Questions and replies are randomized. I made the questions myself. And sometimes they'll have random numbers. Sometimes it'll be a random question on the exact same topic. So yeah, no two students will have the exact same questions. I pulled out you can do an example problem before it lets you do the actual problem. And because this is a test and not a homework assignment, before I gave you 6 attempts to get it right. In this case, you just have one shot to get it right. It's completely multiple choice. All questions have a single chance to answer correctly. There's no sig figs, so there's Perl programming going on behind each question. If you see an answer with like 15 decimal places, don't just assume it's wrong. What you're going to do is you're going to work out the answer on your calculator, and then if you don't use sig figs and just use the exact number, you should see that in your choices. I use 10 for gravity. That comes up at least twice. This practice test is 12 questions. I gave you 30 minutes to do it. The actual test will have 20 questions, and I believe I'm going to give you 45 minutes to do it. So, number 1, a ball is dropped from rest, falls to the floor. The initial gravitational potential energy of the ball-earth floor system is 10 joules. The ball bounces back to a height where the gravitational potential is 7 joules. What is the mechanical energy of the ball-earth system the instant the ball leaves the floor? So you can pause the video and think about it yourself, but over here, just some quick notes. This topic requires knowledge of energy, free fall, and momentum. So here I have a picture, when the ball's up at some height, it has potential energy. And then the instant before it strikes the ground, it has kinetic energy. If there's no wind resistance, these two are going to be the same. Then there's a bounce, and then it's the same thing going back up again. The kinetic energy is going to turn into potential energy. So we have 3 conditions. We have during the fall, during the collision, and then on the way back up again. So before the bounce, in free fall, kinetic energy equals kinetic energy during the fall, except for wind resistance, which is minimal in this case. During the collision, momentum is conserved in an elastic collision, but in this case, we cannot measure how much the Earth has moved. So this is a difficult question because normally we want to say, okay, momentum is conserved, but we can't measure the total momentum of the system in this case. Energy is theoretically conserved in an elastic collision also. So stick together, energy's lost. In this case, we would say, oh, okay, energy's conserved. But in reality here, so not the theoretical condition, but in actuality, energy is lost in the bounce due to heat and sound. So they're telling us that after the collision, we now have not 10 joules, but we only have 7. So after the collision, work and energy are scalars, despite being able to, okay, so after the collision, Ke equals Pe again, except for wind resistance. So it has 10, it fell, has 10 here again, bounced, has less than 10, goes up to 7. So the Ke at the bottom must also have been 7. So where the energy and the momentum was lost was during the bounce. Number 2, we have a graph here, force versus position graph. So whenever we see a graph, we should think of 3 things. Just reading the values. What is the slope? Does it have any significance? Area under the curve, does it have any significance? So in this case, it's force times position. So force versus position, rather. So the area under the curve, of course, is going to be 1/2 base times height. But it's going to be this variable times this variable. So force times position or distance, if we start at 0, force times distance is work. So the area under this curve is going to be work or energy. And actually, if this was a spring, then thinking about Hooke's law, the slope of this line would be the spring constant. So the graph represents the net force of an object versus position. If the object starts from rest and obtains a speed of 1 meter per second after this distance, 0.09, find the mass. So, gee, how am I going to do this here? Well, it's not telling us it's a spring, but I have force, I have position. The area underneath here is going to represent the work. And I have an object that's starting from rest, and it's obtaining this speed. So that's going to be kinetic energy, a starting kinetic energy of 0, and then it's going to speed up to 1 meter per second, so that's a new kinetic energy of 1/2 mv squared, and it's going to get that energy from the joules here, and the energy that's represented by the area under the curve. So this problem is force, work, energy, Hooke's law. Work is the parallel component of the force times the displacement, or in other words, W equals Fd when they're both parallel. So just a reminder here, what would the slope? Well, it's the spring constant. If this is a spring, what is the area? It's the energy stored in the spring, or the work done to move an object. So work is force times distance. And also, the work is going to turn into kinetic energy. That's 1/2 mv squared. So setting these two equal to each other, the force times the distance apparently gave me 0.27 joules. I'm not showing that, but I'm going to set that equal to 1/2 mv squared, solve for the mass. Comes out to be 0.54 kilograms. In this particular case, you'll get different numbers when you try it. In 3, I have a spring and I have this mass up at this position, and then the person stops holding it gently and the spring falls down to this position. Person holds a 4 kilogram block at position A on an uncompressed spring that has a spring constant of 500. The person then lets the weight of the block compress the spring to position B. What is the change in energy of the earth block spring system? So when it's up here, the block has mgh, and because the spring is at its uncompressed length, there's no energy in the spring at this point. That's the position where the spring wants to be. And then here, the block has a different mgh, and now the spring is compressed. So now there's a 1/2 kx squared. So I want to take these two energies, gravitational potential plus the spring, which is 0 on the left case, and I want to compare it to the mgh here at a lower height and the amount of energy that's now in the spring. So this is an energy, work, and Hooke's law problem. Potential energy is mgh. The energy in the spring is 1/2 kx squared. So, I mean, you can just jump right to the answer by using the change in height, but we can also look at the condition before. So in the before case, I have mgh plus 0, comes out to be 12 joules. In the after case, I have the new mgh, comes out to be 8, and then I have the energy in the spring, which comes out to be 2.5. So I have a total energy in the position B of 10.5, and I then subtract the two, and so the answer comes out to be 1.5 joules when I subtract the two. Number 4, I have elevator problem here. The stack of boxes shown in the figure above are inside an elevator that's moving upward. The masses of the boxes are given in terms of the mass of the lightest box. So this elevator is moving up. So we need to think about, well, is it accelerating up, or is it going up at a constant speed? Or I guess constant speed down or accelerating down. The question in this case is, how does the magnitude of the force exerted by the top box on the bottom box compare with the magnitude of the force exerted by the bottom box on the top box for each of these stacks. So in other words, the normal force pushing down on the bottom and the normal force for the top block that's pushing up from the bottom block. Right? Well, this is just Newton's third law. These are always going to be equal. So over here, this problem is forces, gravity, normal force, apparent weight, and Newton's laws. Newton's third law is the action-reaction. It tells us that regardless of the elevator accelerating or not, those forces are going to be equal. So however hard the top block is pushing the bottom, that's going to be equal to the bottom block pushing the top. Now I do want to consider an apparent weight in general, even though it wasn't asked in this question. So, you know, maybe I'm asking what's the apparent weight or what's the normal force or something else. So if I were to look at the bottom block, there's three forces on this bottom block, right? So the bottom block is being pulled down by gravity, that's one force. It has the floor pushing it up, that's the second force. And then there's a normal force due to the top block, that's the third force. So it's got two forces going down, gravity and the normal from the top, and has one force going up, which is the normal from the bottom. So there's three forces on the bottom block: gravity, normal from the floor going up, normal from the top block going down. If the elevator is moving at constant speed, then the sum of the forces in y must equal 0, right? So somehow all three of those forces must cancel out if the elevator is moving at constant speed. If the elevator accelerates up, then I would set those three forces equal to ma and solve for whatever the problem is asking. Question 5, we have this seesaw teeter-totter. So this is a torque problem. A uniform plane. A uniform plane is placed with the pivot at its center. A block is placed on the left as shown here. Balancing the blocks depends on both masses and both distances. So I need to know the torques, right? And torque is force times distance. So in order to know where to put this, I have to consider his mass, because mg is his gravity, and there's the force, and his distance, and then his mass to find his force of gravity and his distance. So both masses and both distances. So I just simply wrote torque is the perpendicular force times the radius. T is Fd, so we need to know the mass and the radius. This problem I remembered from class, but I've got this block being held in place. A block held at rest against the wall with friction as shown in the figure. What has to be true? So what I'm really asking here is what's going on in the x and the y. So I have this force coming in at this angle theta. So x is the horizontal because, x is the horizontal. So in this case, cosine is the adjacent. And because cosine is always the adjacent, cosine is going to give me the x component. So in the x component, in the x direction, I have f cosine theta pushing to the right. I have the wall pushing back to the left. So the answer is f cosine of the angle equals the normal force. Sum of the forces in x must equal 0. Therefore, f cosine the angle equals the normal force. Had I asked a question about the y, sum of the forces in the y must also equal 0. Therefore, f sine theta is either gravity plus friction or gravity minus friction. How do I know if it's plus or minus? Well, if this f is the maximum, then gravity's going to oppose that motion, and it's going to point down. Friction's going to oppose that motion. It's going to point down. If this is a minimum, then friction is helping it to stay up, and friction's going to point up. So in this case, we cannot be sure if friction is up or down without more information. F's a maximum, friction points up. F is a minimum, or F is a maximum, friction points down. F is a minimum, friction points up. Onto this energy problem. The graph above represents potential energy as a function of displacement for a spring oscillating in simple harmonic motion with amplitude x naught. Which of the following represents the kinetic energy of the object as a function of displacement? So the simple answer is here the potential energy is a maximum at the amplitude, it's a minimum at the center, so the kinetic energy is going to be exactly opposite that. So in explaining this, right, this can represent a pendulum or a spring. So looking at the case of a pendulum, it has, at its highest point, it has no kinetic at all potential. At its lowest point, maximum kinetic and minimum potential, and it just oscillates back and forth. So this here is showing that the potential energy U is a maximum at the ends, minimum in the center. Kinetic would just be opposite this. And obviously the same thing for a spring. When the spring's unstretched, then it has an energy of 0. If you stretch it beyond that, it now has 1/2 kx squared. So kinetic is a maximum in the center, and potential is a maximum here at the most stretched position. Here it's going back to the equilibrium position, but then it would again overshoot, and it would be compressed here with 1/2 kx squared again. So if you get a simple harmonic motion problem, it's most likely a spring or a pendulum, or it can be used with rotational kinematics and dynamics as well. This graph is showing potential energy versus distance. The amplitude is x naught. At the center, the potential energy is 0. At max positive x and negative x, the potential energy is U sub naught, the maximum there. All right, next I have this cart that's filling up with rainwater. A cart is rolling without friction towards the right as rain falls into it. As the cart gains mass due to the rainwater, its momentum actually remains the same. It's going to slow down because it's gaining more mass, but the momentum, especially in the theoretical, is going to stay the same here. So, I skipped 8. So let's just talk about 9 first. So as the cart moves with some initial velocity, it is slowing as it gains mass. In theory, this is an inelastic collision, meaning energy is lost. However, momentum is conserved. In general, momentum will always be conserved in the theoretical case. The only time you might have momentum lost is when the Earth or a super heavy object is involved and the momentum gained by the massive object is immeasurable. So it's a stick-together problem, but momentum is conserved, so as it gains mass, velocity goes down. But I was asking what happens to the momentum? It remains the same. Doubling back to 8, 3 forces act on an object. If the object is in transitional equilibrium, which of the following is true? Well, if it's in equilibrium, then the vector sum of all 3 forces must equal 0. So in this class, we don't do much in the z direction, but I mean, the z direction does exist. When an object is in transitional equilibrium, that means the x and y and z forces all equal out. The object is either at rest or moving with constant velocity. On to 10. A railroad car of mass m is moving at constant speed v when it collides with a second railroad car of mass m, which is at rest. The 2 carts lock together and move along the track. The speed immediately after the collision can be expressed as, and then I've got this crazy thing here. Where does that come from? Well, this is going to be a stick-together problem. So the momentum before equals the momentum after. So in general, mv plus mv equals mv plus mv. And it's inelastic. So here's the one railroad car, the other one's not moving, that's 0. And here's what it looks like when it sticks together, m plus m, v final. So I divide both sides by m plus m. And so the velocity would be mv divided by m plus m. In 11, a student weighing 880 newtons climbs a rope at a constant speed to the top. Student weighing 880 newtons climbs at a constant speed to the top of an 8-meter vertical rope in 8 seconds. The average power extended by the student to overcome gravity is most likely. So we didn't talk a lot about power just because we never finished the electrical unit, where I like to introduce power. But power is work per unit time. It is a scalar. So power is work per time. In this case, work is force times the distance. He's moving at a constant speed, so his net force is just his weight. So 880 newtons times the distance, 8 meters, divided by the time, which was 8 seconds. Just randomly, the numbers came out real nice here. So 880 watts. Power is measured in watts. And the last one, a solid metal ball and a hollow plastic ball of the same radius are released from rest in a large vacuum chamber. When each has fallen 1 meter, they both have the same speed. So what's going on? I've got a heavy ball and a light ball. They're in a vacuum chamber, so there's no friction. So number 12 is a free fall problem. All objects near the surface of the earth fall at a rate of 9.8 meters per second squared in the absence of wind resistance, but acceleration wasn't one of the choices. So they're going to have the same speed because they both fell the same distance. It's not inertia because the heavier ball has more inertia. It's not momentum because momentum is mv and the heavier ball has more mass. It's not kinetic energy because kinetic energy is 1/2 mv squared and the heavier ball has more mass. And it's not potential energy because potential energy is mgh, and again, the heavier ball has more mass. So the best answer there is speed. Okay, so this video went a little bit longer than I wanted it to, but please try these problems on your own. Those that have randomization will be randomized, but hopefully this helps you. And again, this is 12 questions, and on Wednesday, I'm going to have a total of 20.